Good morning. My name is Lilly Fang, and my teammate for this challenge is Mackey, and we're really excited to be here today and to present to you our approach to predicting ALS progression for the Prize for Life challenge. So just to recap the setup of the competition, the challenge was to predict the progression of ALS over time for each patient, and this is motivated by wanting to distinguish from fast progressors like Lou Gehrig from slow progressors like Stephen Hawking. ALS progression was measured as the slope of the ALS functional rating score, and this is based on 10 questions. So for each question, a patient would be rated on their ability to perform a particular task, like speaking, dressing, or handwriting. Each question is rated on a scale from 0 to 4 for a total score range of 0 to 40. For a final solution, we had available 918 training patients and 279 test patients. Each patient had about 12 months of data. Much of this was time series data measured at about roughly monthly increments. And our final solution was tested on 625 validation patients for which we only had the first 3 months of data. And again, the goal was to predict the ALS-FRS slope for months 3 through 12, given only data from months 0 through 3 for the validation patients. And the performance was measured as the root mean square deviation of the predictions. So just to give a quick roadmap of our talk today, I'll be talking about our featurization approach, and Lester will follow with a description of our model and its performance. So the goal of featurization is to come up with a compact numeric representation for each patient, and this will serve as the covariates in our regression model. Our strategy was just to extract as many features as possible, knowing that a lot of them would be irrelevant, and then to rely on the learning algorithm to identify the most predictive features and deal with the irrelevant ones. As Hans mentioned earlier, the data is in 2 categories, roughly, static data and temporal data. So for static data, this is data that's measured just one time for each patient. It includes things like demographics, ALS history, and family history. ALS history in particular includes variables like the time between onset of the disease and the start of the study, which turned out to be a very predictive feature, as well as the site of onset. Featurizing static data is fairly straightforward. All we did was code categorical variables as binary indicators, and we could use all of it that way. We ended up with 49 static features. Temporal data, on the other hand, consisted of measurements over time. This was the vast majority of our data. So it included the ALS-FRS question scores, alternative ALS measures related to lung capacity, like forced and slow vital capacity, and vital signs data. And of the vital signs data, we used weight, height, blood pressure, and respiratory rate. Also available in the temporal data was a number of lab test measurements, but we ultimately did not find this to be useful, so we didn't use it in our model. Because the number and frequency of the measurements varied across the patients, somewhat less straightforward to come up with a common set of features for each patient. Our approach was then to compute statistics from each time series for each patient, things like the mean, max, standard deviation, and use those as features instead. We also computed pairwise slopes of the data to try to capture a sense of the rate of change of each variable, and then extracted the same statistics. So to illustrate, here's an example where I have ALS-FRS score data for the first 3 months. Here it's at 1-month increments. And I can just extract summary statistics like I talked about earlier. We did many more than this, basically everything we could think of. And that way we can have a common set of features over all patients, regardless of how many measurements they had in that 0 to 3 month period and when those measurements were taken. In particular, we can also calculate an overall slope over the 0 to 3 month period. You might imagine that might be predictive of our target prediction, which is the slope over months 3 through 12. We can further compute pairwise slopes on the same data. So for example, here our first pairwise slope data point is -1, and that's between the first score data point of 40 and the second data point of 39, and that becomes a new data set entirely from which we can extract the same statistics. Here I'm just plotting it on the secondary axis. And we associated each of these pairwise slope data points with the midpoint date relative to the two endpoint dates. And here again, we're just calculating the same statistics on here, including the overall slope of the slopes from 0 to 3 months. Using this approach, we came up with 435 temporal features, which is almost 10 times the number of static features we had. And notably, one big problem that we had to deal with was missing data. There was a lot of missing data in this challenge. To give you a sense of the magnitude, the average patient was missing 10% of his or her features. One patient in particular was missing over half their features. And what we did here was simply to replace any missing values with the median feature value of all the data that we could see at that point. So now I'm going to hand it over to Lester. We'll talk more about our model.
Hello. Can you hear me? All right, thanks, Lily. So now we have a way of featurizing the data from each patient, and we'd like to adopt a regression model to map patient features onto patient slopes. So generically, we'll assume that the future ALS-FRS slope is equal to some unknown function, let's call it f, of the patient features plus, let's say, Gaussian noise. And our goal is just to infer f from data. Now, if we were Bayesian, this would just amount to basing a prior distribution on f and then inferring its posterior. And one advantage of this approach is that we have, in addition to our predictions, estimates of the uncertainty around those predictions. Okay, so let's be Bayesian. Our first step is to choose a prior. And we'd like this prior to be both flexible and non-parametric, so that we don't make too many assumptions about the functional form. For instance, we don't want to assume it's linear or has a particular functional form. And we also like a prior that favors simple, sparse models to avoid overfitting to the large number of irrelevant features that we'd extracted in the first phase. So we adopt a particular approach due to Chipman, George, and McCulloch. It's the Bayesian Additive Regression Tree approach, or BART model for short. The BART model assumes that their function f is a sum of simple decision trees. So you can view a single decision tree as a rule for predicting slopes given only a few features, a few of your input features. So, for example, you might have a single decision tree that computes the number of days since the onset of ALS. A large number of days is a good indicator of actually slower progression. So this decision tree might predict -0.5 for the slope of such patients. A smaller number of days is an indicator of faster progression. So the decision tree might predict a larger value, or a larger magnitude value of -0.83. Now this crude rule by itself might not lead to very accurate predictions, but combined with other decision trees that operate on different features of your data, we can create more elaborate, more flexible, and more accurate decision rules. So in particular, you might have a second tree that operates only on the past, that is 3-month ALS-FRS slope, and use that to offset the prediction of the first decision tree. And we can add more and more to create more predictive rules. Okay, and by simple here, I simply mean that each tree depends only on a few features, and this is enforced by the BART prior, so that irrelevant features are seldom selected by any particular tree. I should also note that this is very similar to various frequentist methods, common ensemble methods like boosted decision trees, and random forests. Okay, so now we have a prior, and our goal is to infer the posterior under that prior. We use a standard BART package that's available on the comprehensive R archive network. It's called BART, and it uses Markov chain Monte Carlo to draw samples from the posterior distribution over F. So in particular, in our method, we draw 10,000 posterior samples. We'll call them F hat 1, F hat 2, etc. And recall that each sample is itself a sum of several decision trees, in our case, 100 decision trees. So this might seem like it would take a long time to draw 10,000 samples with 100 trees each, but the whole process only takes about 10 minutes on my laptop, a MacBook Pro. And given these samples, we can then form posterior predictions of any given patient's slope. So each sample has its own estimate of the patient's slope. We take the average of those to find the posterior mean. And because BART itself is a stochastic procedure, we further reduce variance by taking an average across the predictions of 10 independently trained BART models. So just to illustrate the performance of BART, I've here trained a BART model on our training and test sets and validated the model on our validation set. The blue curve here represents BART performance. The red curves represent standard error around the BART performance. And I've plotted a BART performance as more and more samples are drawn from the posterior. So after one sample, BART has pretty mediocre performance, just about 5459 RMSD. After 100 samples, this performance drops to about 5234. After 2,000, we're already down to 5144. This is actually a good score relative to what we've seen in the contest. And after 10,000, we get down, this is from a single BART run, down to about 5109. Okay, and again, this whole process only takes about 10 minutes. Now, in addition, BART can be used to extract the utility of different features by simply counting how often each feature is used by one of its component decision trees. So here I've displayed the top 10 features ordered by usage from a single BART run. And this actual top 10 can vary from run to run, but we do see some consistent patterns. Also, for comparison, here's a plot of the usage of all 484 features that were given to BART. And you see that the top features, the first few features, are actually used much more often than those that come afterward. Okay, so one pattern that we've noticed across BART runs is that onset delta, that is the time elapsed since the onset of the disease, is always the most used by the BART model, much more used than any other feature. And we find that larger values of onset delta, that is more days elapsed, typically indicates slower progression of the disease. Other highly used features include the maximum score reported for the dressing ability. This is one of the ALS-FRS functional scores, as well as the 3-month slope in ALS-FRS in the past, and the last recorded pairwise systolic blood pressure slope. In fact, it's interesting to note that about half of the top 10 used features are these pairwise slope features that Lilly described earlier. And note that also that lab data does not appear here. We did not use that in our final BART model because we found that it either did not improve performance or in some case made performance worse. Okay. So to investigate the impact of each of these highly used BART features, we retrained our BART model using smaller subsets of features that were identified by the larger BART model. So we began by just training a BART on a single feature, onset delta. And you see that with just one feature, you can already achieve an RMSD of 5291. Okay. Then we retrained the BART model by adding in the second most used feature, that's max stressing. And we found somewhat surprisingly that actually hurt BART's performance. But then the third feature, the slope in ALS-FRS over the first 3 months, improved performance to 5246. So we repeat this process over and over again, adding in one feature at a time. After the fourth feature, progress again is hurt, but the next 2 features add a great deal to the predictive performance, so that by the time we're incorporating 6 features into the BART model, we have a performance of about 5190. We can do this over and over again. The next several features actually only negatively impacted performance, but last speech, last handwriting, and mean square speech all strongly contributed to the final BART performance. So after 14 features, performances increased to 5157. And after 21 features, we're already getting an error of 5113. So this is basically comparable to the error of the BART model on all 484 features. So you can actually get away with a much smaller subset to obtain the same predictive capacity. Now, we don't know the exact relevance of each of these features to our final outcome, that is future ALS-FRS slope, but we hope that highlighting these features will be useful for future clinical research. Okay, as a final comparison, we wanted to study how other models would perform using the same feature set that we extracted for the BART model. So we have 2 testing scenarios. The first is to train only on the training set and to test on the test set. And the second is to train on the training plus test set and then to test on the validation set. So this is the performance of the BART model in each of these cases, 4860 on the test set, 5109 on the validation set. And when available, we'll also report competitor RMSDs, that is the performance of algorithms run by competitors on their personal feature sets. So we ran lasso regression using our feature set, and we found that, well, performance degrades in both cases. Typically, well, yes, we find that both test set and validation accuracy is worse using lasso regression, which is just linear regression with an L1 penalty on the weights. We find that random forests actually obtains worse performance on the test set, but much better performance on the validation set. And actually, the performance of random forests using our features is comparable to BART on the validation set. And just for comparison, These are the known RMSDs for other competitors and their feature sets also using random forest. So they lie in the 5.2 to 5.3 range. Finally, we also implemented a boosted decision tree algorithm using our feature set, and we find that performance is pretty much comparable to BART performance, although BART is slightly better. So a couple of takeaways from this are first that these additive decision tree models, that is BART, boosted trees, random forest, they all have the same functional form, are especially effective on this data set. And second, that featurization seems to be a primary differentiator among different competitors, and that the same models can be used, but different feature sets can lead to different error ranges. Okay, so that is our talk, and if you have any questions, we'd be happy to answer them.
So Lasso did not perform quite as well as your model.
That's right.
But the difference, it seems, was only about 4% in RMSD, right?
Right, so there's still the question of, so we're reporting these differences, and there's still the question of the significance of these differences. And I think so one of the early talks addressed that, and you might still believe that these differences are not very significant. But we do find that certainly the ordering is significant, that BART will always perform better than the linear regression model.
But just in practical terms, a Lasso method is maybe conceptually a bit simpler than a stochastic, semi-stochastic method like BART. So, in practical terms,
that's right. So one might prefer one over the other, maybe. I think it's a very reasonable point. One interesting thing is that even with, so Lasso is very simple in that it often selects a very small subset of the features. It's interesting that you could do something similar with BART as well and obtain, say, a small feature set like the 21 features that I mentioned to get a very concise model. But in terms of clinical relevance, I'm not well equipped to address that.